All right, this is it. This is our final lecture for the first half of the class. It is going to wrap up our discussion of tables. So up until now, we've talked about 2 by 2 tables, sets of 2 by 2 tables, arbitrarily large tables, and then, right, you guessed it, we're going to round things off with a discussion of sets of arbitrarily large tables. So we're going to talk about sets of S by R tables. An S by R box crafted by rows and columns. Inside, infinity. An S by R box crafted by rows and columns. Inside, infinity. An S by R box crafted by rows and columns. Inside, infinity. You probably saw it's a short video. It's a short set of slides because the extensions are very easy. We've done all of the heavy lifting. Just like before, we look at the individual tables that comprise our set, and we ask ourselves, are either of the variables ordinal? And if they are ordinal, what should our scoring be? So remember, if both variables are unordered, we're going to use a test of general association. That's still, right, even if we have a bunch of these tables, it's still our overall aggregated test statistic will have S minus 1 times R minus 1 degrees of freedom. If the column variable is ordered but the rows are unordered, we'll use a row mean score test. Again, even a set of those, a collection of those, still has just S minus 1 degrees of freedom. And if both variables are ordered, then we're going to do a test of correlation with a 1 degree of freedom, right? We've done all this before. Check, check, check. Having sets of tables helps with our sample size requirements. So all those rules of thumbs that we had from our last lecture, we apply those to all of the tables added together. So we kind of apply them as if, like, right, everything in our stratifying variables all lumped together into one large table. So conceptually, right, it's this idea that we've already seen, right, just like with our sets of 2 by 2 tables. We consider each table to follow this multivariate hypergeometric distribution, right, on our usual assumptions of conditioning and null hypotheses. And for any one of those 3 situations that we mentioned, we combine data across the tables to produce an aggregate overall test statistic. Now remember, when we're making our conclusions, we don't want to forget to communicate that these conclusions are after controlling for our stratifying variable or variables. Now, unlike our sets of 2 by 2 tables, we do not have, there is not a generalized test of homogeneity. The idea of an odds ratio is unique to a 2 by 2 table. So we can't look at this idea of, like, do the different tables have a common odds or common odds ratio? So sadly, we don't have a generalized extension of the Breslow day test. All right, so we're going to just do one example, and then I'll have some extra examples for you to do on your own. So this example came from a real-life study by Stokes in 1986. It was conducted to see whether or not colds are more common in urban or rural areas, and he wanted to control for potential gender inequities. So, right, two genders gives us male, female, and we have some 2 by 3 tables. So we have a set of 2 by 3 tables. I guess we really should call it sex, not gender. I apologize for that. My bad. Wanted to control for sex, not gender. And for sex, we have male and female. And so there we are. So here's our code, proc freak, our weight statement, gender, by residence, and by cold. And of course, to get the output, we would add the CMH output. The CMH option will get us like the relevant test statistic output. Right, and so here's our table for females. Right, so so first off, which of our tests do you think is going to be appropriate? Well, we have ordered columns and unordered rows. So that's going to be a row mean square test. Agreed? What's the appropriate scoring? Well, here, this is our first example of something that does have equal spacing, right? The difference between 0 colds and 1 cold is the same as the difference between 1 cold and 2 cold. So we're going to use the row mean score test with table scores or integer scoring. Now, do we meet our sample size requirements for this table? If we're looking just at the female table, and the answer is yes. Our row totals are more than 20, and our cell totals are more than 5, so we don't even have to worry about collapsing. Let's go ahead and look at the male table. Down at the bottom there. The male table is, the row totals are also more than 20, and the cell counts are more than 5. So, right, even if like what our male or females had, for example, row totals less than 10 or less than 20, that wouldn't necessarily be a deal breaker because, right, these rules of thumbs are actually applied to the larger table in which we have males and females combined together. So we really just need the combined row totals to be more than 20 and the combined cell totals to be more than 5. And of course, if they're not, we can try that collapsing mechanism. But in this case, since both of our individual tables satisfy the requirements, certainly the aggregate table does as well. So our sample size requirements are met. And so here's our overall test statistics, right? Notice it says on top, controlling for gender. It's reminding us that these test statistics are controlling for that stratifying variable. So there's our row mean scores test. It's got 1 degree of freedom, right? Because we have 2 rows. 2 minus 1 is 1 degree of freedom. We have a large p-value, 0.3903. So that's going to mean that we fail to reject the null hypothesis, at least at the usual 0.05 level, which means that the average number of colds does not differ between rural areas and urban areas, even after adjusting or controlling for gender, or sex, I should say. Yeah, so the appropriate test is the row mean score test. We already talked about why that's the case. We already talked about why the sample size is justified. If you looked at that last thing, if you looked at the last bit of output, SAS always tells you which scoring it uses, and I should have pointed out, go back and take a look. It says table scores. That means integer scoring, and that is appropriate because we have equally spaced categories. So our null and alternative hypotheses are, right, null hypothesis that the mean average number of colds after adjusting for gender is the same for urban and rural areas, and then the alternative is that that mean number is different between the two. Almost like a generalized t-test in this case. We saw our test statistic was 0.7379. It had 1 degree of freedom. Its p-value was 0.3903. So we would say after adjusting for gender, there is no difference, no significant difference in the average number of colds between rural and urban areas.